Hey there, class. How's it going? We're on to number 4 now. So, yeah, let's dive into it and we'll see what we got. With this one question in particular, though, just want to give you a heads up. There's a couple of ways that you can possibly do this. I updated the answer key to be a little more clear, hopefully, and I'm going to post, similar to the last question, a second follow-up to this walkthrough in order to explain how some of the alternatives work and how you can derive the equations to arrive more or less at the same question. But also for those of you that are able to grasp that and that helps, is it might link up a few of the equations and a couple of the concepts as far as how some of our linear equations that you have on your sheet relate to projectile motion, because again, of course, whenever we have some sort of projectile object, we break it down into the x and y axes all the time, always, right? Unless we're looking for the composite, but that'll be a very specific question that will ask you for that. So, okay. That was my preamble. Let's get into things. So we're looking at a question here. We have a soccer ball at rest. So I'm going to draw it over here. So here's our soccer ball. It's resting on the ground. And someone comes along and chips it. So that's kind of like you get under the ball and send it up at a fairly high angle, which is kicked into the air. And has a resultant velocity. So resultant is both the x and the y together. So that's talking about an angular one. So it's going to chip it at a fairly high angle at 7 meters per second. And the angle to the field that this person is chipping the ball up here, that angle, or theta, equals 84 degrees. Okay. So 7 meters a second at 84. So we've been given a magnitude of some sort of a velocity with a direction. So it's definitely a vector velocity. If the ball experiences a constant vertical acceleration of negative 9.8 meters per second squared, so that's our gravity constant, right? We can put that in. So we can write either acceleration or gravity, A or G, doesn't matter. And we go minus 9.81 meters per second squared. Okay, so we got that part now. From there, that's supposed to be squared. Okay, so that's kind of all the information we've been given so far. So let's look at A. Got our system drawn, perfect. Collected what we knew, great. First two things to always do with word problems, always. A, what is the vertical velocity? So the y-axis. What to start with? The vertical velocity, sorry. And the x-axis, or y-axis. Great, okay. So what we can do when we look at our equation sheet here, we come back to it, and whenever you're talking about velocity and angles and what is the resultant or component, you really should just hone in right away into these two equations and try to figure out which two from there. I've actually given you a little extra bonus cue kind of information that normally isn't really given, but right here in the subscript you can see either a y or an x. So that's telling you that what you're solving for in that is the x vector velocity vector or the y velocity vector. That'll always be the case relative to your angle. If you really want to figure out how or why that is, You can use SOHCAHTOA to figure that out, but I'll just use one of the two maybe as an example just to explain that a little bit. So if this is our angle here and that component, if we were to make this a triangle and have two other components, so we have our, let's say, x running along there, and our y running here, again just going tip to tail. I should have used a different color for that. Don't want to get it confused with gravity. Okay, so we have our vertical y and our x velocities. Here is what we're looking at. We want to figure out the y, right? So we can see its sign in the equation. So v is just the angular component velocity, so the 7 meters per second. So what we'll have is sine relative to the angle here that the ball's being projected up from is opposite over hypotenuse. So if we go the opposite from this angle, that's this, our y, and our hypotenuse is this right here. The 7, this is a right angle triangle, this is our 7. So again, if we just rearrange this component, it'll be, again, opposite over hypotenuse, and we know our hypotenuse velocity here, so what we're trying to find is the opposite, which equals our y velocity. Okay, this is our hypotenuse velocity. Look at it that way. Okay, so that's why we use sine. That's what we know. That's what we're trying to figure out. Okay, so let's move forward here with this information. So again, I give you that little secret note, or that little extra help there with that equation, so we know right away. We just look at our equation sheet. As soon as we see a velocity that we got to figure out one of the individual components from, or the that's our go-to. Okay, so what we'll do is from here we go our velocity of y, so we're looking for the vertical, is equal to v, let's write it all out, sine theta, and again you can draw that in just to make sure you calculate well. So giving us some actual numbers here, that equals our initial velocity, which is 7, times sine times 84. And when we calculate that out, we find that sine, I'm just going to write this out because it's actually an interesting number, rounding up, we get 0.99. Okay, so it's almost 1. 90 degrees would be 1. So again, we're going to go between 90 as 1 and 0 as 0 when you start multiplying with sine. So we get that, and so what we get is a 0.6 something or rather, 0.69 or 7, or sorry, 9 or 8. So when we round up, it ends up just being 7 meters per second. Okay, again, just rounding up from one decimal place. So that's your VY. Maybe I'll calculate for sure just so you can see that. Yeah, so it's 6.93. Again, yeah, we could leave it at that, or round up. So I guess for this, let's just go with that. So here, there we go. Great to be more complete there. Okay, great. Yeah, okay. So that's part A that we figured out up here. Okay, let's move on to part B. What is the ball's position in the air after 0.9 seconds? Okay, again, this part There's a few alternative ways to do it. I'll try to do it in a little bit more of the roundabout way or the fuller way, and then some of the more shortcut derivations that maybe people caught or used, I'll do in the next video. Okay, so again, here's B. Let's start off with reading the question. So what sort of information do we have here? So whenever we're trying to figure out what equations to use, one of the reasons we get all of our variables that we can collect to start with is it gives us a clue to what equations we can use, in particular with the kinematic equations. I like to say trying to figure those out is a little bit of like a logic puzzle, in the sense that you're trying to figure out which one of the equations has all the variables that you need with only one unknown. And so you'll find one of those equations, and typically one of them will also have not something that you don't have. So I'm going to say that one more time, just a little differently with some actual examples. So for example, one of the things we're looking for is a change in position. Now just remember that with vertical velocity in a projectile motion, we can just treat it on the y-axis, so up and down. But depending on how we state which direction our system is we could turn that system either way we want. So it could be an x-axis, it could be a y-axis, depending on how we designate things. Okay, so if we take a look over here at the equation sheet, just because something says y doesn't mean that we can't necessarily use it as x. Okay, similar up here. If something says x, essentially we can just turn our system to make it orientated the way that we want it to, and we can use those questions, those equations. Okay, so let's track back to our sheet here. We're going to take a look at what we have. So again, just as a reminder, we now know, based off of our last equation, our velocity on the y-axis. So we can think of that as up and down, right? Or up primarily, sorry. Just think of it as up. Okay. As positive. Okay. And that equals 6.9 meters per second. Okay. So if it's 6.9 meters per second that we have on our velocity, our vertical velocity for this equation, what we can then look at is time. So time equals 0.9 seconds, which we're given. What else do we know? We know acceleration. So acceleration is equals to 9.8 meters per second squared. What else do we have? Do we have change in y? No, that's what we're looking for. Ball's position after it's been in the air for 0.9 seconds. And what other variables do we have? Usually not anything else. Okay. And just as a reminder, anytime you see like a delta x or delta t, it's always equal to x final minus x initial. So you can always take those variables and convert it into that, or vice versa. You can take this variable and split it into tf minus ti if you have one of those two variables. Okay, that's just a little side note. Let's refocus in back on the question here. Okay. Great. Okay, so we can start looking at our equation sheet here, the variables that we have, and what we're trying to look for. So the one thing we also don't have is V final. Okay, so this is our V initial on the y-axis. Okay, so vertically speaking, maybe that will help us as too if we say vertical there, okay? Vertical. Okay, so now that we're organized, again, we don't know. Okay, so now that we're organized here, we can look at our equations. And now, when we're looking at projectile motions, one of the places we can start at is down here. We're looking at these equations. Okay, so I remember that acceleration can also equal g, so it's all the same thing. So that I have. Do I have time? Yes. Do I have the change in velocity? No. Or change in displacement? I don't. Okay, so that's a possibility. But one of the reasons I don't want to use this time around is because it doesn't say anything about my initial velocity. It doesn't include me at this starting point. In fact, this equation assumes that there isn't any initial velocity. So this is part of our free fall equations. So can I use that? No, unfortunately not. Let's keep looking through these, okay? So now I have this equation. Okay, delta t, or let's go velocity final. I don't have that, okay? So right away, that kind of raises a flag for me because I'm like, okay, I don't have velocity final. I'm looking for a change in position. So already, one, there's not even any delta y in here. There's no delta x, and there's no, I don't know the velocity final. So there's there's not even the variable I'm looking for in here. But two, I don't even have, if it did, I'd be missing two, I'd have two unknowns, and that's not a good situation you want to be in. Okay, so let's keep moving forward. Next one, we'll check it out. Okay. So delta y, great, that's in there. That's exciting, that's good news. That's what we're looking for. So I potentially could isolate this somehow from the rest of the equation. Great. Gravity, definitely we have that. That's involved, that's the acceleration. And the initial velocity we have, good. But now we're looking here and we look, okay, we don't have velocity final either. So now we're back at this situation where we have one unknown and two unknown. We can't solve for two unknowns, all right? So what do we do? What do we do from here? These last two are only looking to points at the apex, either by distance or time, so height or time. So we don't want to look at either of those, okay? So what can we do? That's all our typical projectile motion. Well, I kind of alluded to it a few times. You might have seen it in your answer key. So we need to turn back to our linear kinematic equations that are more familiar for us when we're just dealing with linear motion. Okay. So now we start looking at these. All right. So what are we looking for? Well, we're looking for a change in displacement on the y-axis. And all these have x's in reference to position and displacement, etc. But we can change that. And also we see lots of a's for acceleration, but we know it's gravity. So we can take these same equations and apply them to a scenario where we only care about one direction, right? We only care about the vertical axes. We only care about y. We don't care about x. So it's no longer two-dimensional kinematics, it's one-dimensional. So these equations apply, okay? So what we'll do is we'll try this out. Instead of y, we're just, when we write the equations, we're going to change all x's to y's, and if whatever equation we use from here, we're going to we'll change all accelerations to gravity. We'll just put g, okay, when we rewrite it. Okay, so what we'll do is we're going to go through our list of equations and see what we can figure out, what we can use and what we're not going to use. So just in case I edited this section funny, I'm going to go back and try to check, but we kind of went through each of these already and said that they don't really give us what we want, okay? they kind of come close, but not quite what we need. Okay, so we've gone back up here to the linear kinematic equations, and we're going to try to use that by changing the x-axes into y's, which is fine. It just means we've turned our coordinate system. It's totally okay. We can do that. And change our accelerations to gravity. Okay, we're going to see which one of these match up best. All right, again, our goal is always to find which of those equations use the variables we have, but leaves us one unknown, which is the thing we're trying to solve. So what we're trying to solve here, and just as a reminder, is the change in position, or the other way we could look at it is y final. Okay, but again, just for the use case here, or this example, we're trying to we'll essentially find x final or delta x. Okay, it's all kind of the same. Okay, so let's start going through these and taking a look. So this first one, x equals x naught. Again, it's really easy to move this over here, and then we'll get delta x. So this is promising so far. This is the variable we're looking for. And then we have velocity times time. So we do have a velocity over here, but we don't have a change in velocity, or we don't have an average velocity, right? We just have an initial velocity. So we're missing a piece of information there for this one. Okay, we don't know if the velocity is the same all the way through. Okay, so we can't use that. So we're on to the next one. So we have velocity equals an initial velocity plus acceleration times time. Looks like we're missing a really important part, which is what we're looking for. So our change in position. So we're not going to use that one. Looking at the let's look at the last one here. So final velocity, initial velocity, like it's looking okay because we have this x, or change in position over here, but we don't have a final velocity, so we can't use that one. So we got one more. Let's hope this is the one. Okay, so let's take a look here. So we have x equals x naught plus the initial velocity times time plus half times acceleration times time squared. Okay, so let's go through a little checklist here as far as variables. What do we have? Well, vi, so initial velocity, yep, that's this one right here. Great. We got time, good. There's time here and here, excellent. We have acceleration, or gravity, yeah, right there. Can make that a g right now. Is there any velocity finals anywhere? Nope, none there that we can see, so that's good. And then last but not least, we're looking for delta x. Okay, so that's where you might get tripped up. So just remember, delta x is exactly the same as saying x final minus x initial. Okay, so what we can do with that is essentially we can very simple rearrangement by minusing that delta x and putting it on the other side. So we have x, or x final, minus x naught, or an x initial, and that is also going to equal the same thing. Okay, so that equals delta x. Great. And in this case, again, because we're looking for the vertical axes, remember that we were saying delta x can also equal delta y. It's just how we orient our system, or coordinate system. So again, all of this we can just say equals delta y, and actually let's rewrite this whole equation new now, just as we've changed it and modified it to fit our needs as we need it. So we have delta x, y equals v naught times time, so that can also be initial. That's Yeah, let's keep it that way. Sorry. So v times t plus plus 0.5 times gravity, right? We changed acceleration to be gravity, times time squared. Awesome, that's great. So here we are. We have this equation that will give us what we're looking for. Change in position, matches all our variables. Great, okay. Now, just as trying to tie together what we're seeing here, if you look down here at this, you'll notice it looks very similar, right? The main difference is this component here, okay? So if we just look at this part, and obviously solving for that same thing, and we look at this equation here, holy moly, that is the same thing almost. The only difference between the two is VT. So what is that saying? Why is that the case? What did we just figure out here together? Well, what we found out was the change in position is related to our how acceleration, so again, the gravity of our system when we're looking here, right, is related to our initial velocity over time. So again, this equation here is if something's in free fall. So if something's in free fall, VI equals 0. So 0 times time is 0. So all we'd be left with in a free fall situation would be the change in displacement, or vertical displacement, is equal to this here. Which is, again, it's but our system here has an initial vertical velocity. So that's why we have that in there. So we need some sort of upward moving to start us off here. And what we're going to find is this component is what happens for our downward counterforce. And then we add those together, and that will give us our change in position. Okay? That's more or less what we're saying here. Okay? Okay. You can go back and check that out if you want as you go along. So let's get rid of as much of that as possible. Good. So we're going to return here to our equation that we got, and we're going to start putting in variables that we know to be true. So our delta y equals, in this question, our initial velocity is, vertical velocity is 6.9. We found that there in our previous question. Our time, of course, is 0.9 seconds plus 0.5 times gravity times time again, so 0.9, but we're going to make sure we square that. That's an important part, okay? Great. From here on in, if you got to this point, we just plug and play, right? So the math on that first component, what I had, I used 7, so we'll recalculate that now. So if we go 6.9 times 0.9 equals 6.21, and then the second component should be the same. So when we multiply all that together, we actually get a negative 3.6 9, sorry, 3.969, and that's a negative, again, because gravity is in the downward direction relative to our initial velocity, which has an upward vertical positive direction. Okay, and so again with this, to carry forward, you can round everything up, so that equals 6.2 plus negative 4, which when we do that math, Yeah, okay. You go. So essentially, you go 6.2 minus 4, okay, which equals 2.2. Okay, and so that's the change in y. And so again, just being thorough, making sure you carry through all your units, you get 2.2 meters. Okay, and that's how you do that one. Yeah, and so again, I kind of dove into how we got some of that equation there and how we derived it. In your answer key, again, there's some more examples of different equations. If I'm able to, I'm going to make another video and explain how each of those equations kind of boil down into more or less the same equation that we use to get the right answer here. Okay, I'm going to do the final question first though.